Assalamu alaikum.
Hello, Doctor.
Assalamu alaikum.
Salam.
Assalam wa rahmatullahi wa barakatuh.
Well, I hope a successful and happy new year for you.
Thank you as well to you, Doctor.
Well, really, I think few of you asked me about the data set which I have sent you, the lead exposure data. I will talk a little bit about it, though it was just an exercise. It is, I said, don't consider that exam, but still I will talk really about it. So let's share screen. So, well, so these are really people who are exposed to lead really through their occupation. And really the data deficit in age. I don't know why the age was not taken, but what has taken the sex really and the body mass index really has been taken for estimation of GFR, of glomerular filtration rate. So serum creatinine really reflect renal function, and lead is really this is the independent variable, is the exposure variable, independent variable, or the X. While serum creatinine is the outcome variable, or the dependent variable, dependent, or Y, which reflect renal function. So we said that the question is whether lead exposure affect renal function. Renal function really can be also assessed better by GFR. I think there is an equation, you can see that equation on the internet, which uses serum creatinine, body mass index, and sex in order to estimate GFR, glomerular filtration rate. So really, serum creatinine and GFR, both of them reflect renal function. Well, in a different way. Yani. When serum creatinine increases, it reflects worse renal function. While glomerular filtration rate, when it decreases, it indicates worse renal function. Again, we have lead here, lead and LAAD. So lead really, when increases, it is, of course, it is likely that will affect renal function more badly, while LAD is really the reverse. So LD, when it decreases, really, it means lead is higher and likely effect of on renal function is more severe. So really, these are, they are, if you correlate them, they are disproportional. And if you correlate also serum creatinine with GFR, they are disproportional. But what we want is the ratio between renal function and lead. So really, I will start, if I am analyzing this data, I will start by describing the data. So I'll describe my sample by frequency of male and female, by, for example, mean and standard deviation and range for ALD, for lead. Maybe even I show the grouping. We have two groups here. Even I show serum creatinine level, mean and standard deviation range for GFR or BMI. So I describe the data, then I start to analyze the data. So my analyze really, for example, I may analyze by t-test because there are two groups here, not three groups. So they are being already categorized into two groups. But my analyze by ampere t-test, my analyze difference. I saw there the serum creatinine is significantly different for the two groups of lead. Really, I have written here three groups. They are really three groups. Really, we should correct that. Yeah, we can correct that. Really, there are two groups here. Of course, there were another group. I think there were another group here, but I think this group is not present here. There was another unexposed group. So there was another unexposed group which really have a lower lead level. We can simply remove that. Yeah, we have two groups here. Yes, so we can we can't of course apply another because there are two groups here. So we simply can apply t-test here for the difference between in serum creatinine for the two groups of lead, and then we can also make correlation between show correlation graph and also correlation R correlation or coefficient of variation, coefficient of correlation between lead and serum creatinine. You can also graph the relationship between them. We can again repeat that for lead and GFR. We can repeat again that for ALD and serum creatinine, and then GFR. We see also the relation and the difference, and the difference is or correlation. There is positive or negative correlation, and whether the correlation is significant or not. Some of you really suggested that also they analyzed the sex. Really, it was not in the aim, but probably yes, males are more likely that they have a higher lead level. So probably again you will see whether lead level will be affected by sex, and whether that will affect the renal function, whether male and female are different regarding renal function. So really, it is an exercise. Yeah, and you can also go and also analyze by body mass index. But of course, I want you to not to make so many results. I want you to make few results, really few tables and few graphs, which are useful for an article. One of you send me an analysis. Really, he sent me two SPSS file and Word file, which is really something a copy paste of the SPSS. No, I don't want that. I want a clean. You can analyze whatever you want in SPSS, but at the end, in a Word file, I want you to put few clean, nice tables and graphs which are suitable for your thesis and for an article. Okay. As we see, so that, and we'll see this lecture, there are many results, many results which produced by SPSS, but we usually select of them. We select usually the final table and the p-value to put usually in a suitable, understandable way. I show you how to take the result from SPS and convert them into Word. Usually we don't take everything. The SPS output cannot be put all of it in an article or in a in a thesis. Usually, what we put in an article in a thesis are a clean table, a nice table, and understandable table. Okay, so of course today we'll see how we will do that. We'll see some of the things. We'll see how to obtain a clean result. Now I will close this now. Let's return to. Now today our subject really are two things really. According to our course, we have here linear regression and also logistic regression. They are big subjects really. Sometimes you'll find a complete course in the internet about linear regression and logistic regression. But simply, well, linear regression is this is the equation for linear regression. It's a simple linear regression, which means that only we have one outcome. The outcome is only one, which is, for example, in the lead study, could be renal function in form of serum creatinine or glomerular filtration rate. And here, of course, we have something called alpha or beta 0, which is constant. And we have here the outcome or the exposure variable or the effector or the explanatory variable or the called independent variable. Of course, why called dependent variable? So dependent variable is affected by the exposure variable or the X or the exposure or the explanatory variable or the independent variable. And the independent variable, usually it has a coefficient. Okay, so sometimes, of course, you may have multiple regression. It's a simple regression is only one variable, one independent variable. In multiple regression, you may have multiple x's. Yeah, this would be plus b2 x2 plus etc x3 and b3 etc. So in multiple regression we have multiple variable, while in simple linear regression it's just similar to correlation, only we have two variable. We have the y variable, the dependent variable, and the one independent variable. Okay, and we have this coefficient. This coefficient, of course, can be used in calculation of y when we know x. So suppose now we want to study a relation between, very simple example in this, of course, in this exercise, which is also you can see it in the exercise which I have give you, the training exercises, the training files I gave you for the books or the accompanying the books. They study the relation between weight and height. So you predict the height from the weight or vice versa. Usually, of course, you may have a scale for the weight at home, but you might not have a stereo meter or a measuring tape available on your hand. So you may want to estimate the height from the weight. Okay. So usually, of course, the weight and the height are correlated, and usually heavier person also are taller. So usually the relation, as you see, is proportional, and we can use really the weight in order to predict the height, and or vice versa. Usually try to predict the difficult thing from the simple thing. Okay. So here we have this is suppose this is the weight, and it's a coefficient. So if I know your weight, then I multiply your weight by this coefficient and add the constant and obtain your approximate height, to not be exact. So this is really equation is approximation. It is used to estimate, not to exactly measure your height, but to estimate your height from your weight. Okay. So really it's written as beta. Well, the real coefficient is unknown. It is b. So letter B, which is we don't know it. Usually we have approximation. This is it's a symptotic equation, approximate equation, which is by which we estimate or قدر تقدير, we estimate the y from the x. Really, the constant represent the y when x is 0, as we see in the graph. You see in the graph that when x is 0, then the constant will equal y, or y will equal the constant. So let us see. This is the data for physical activity. Usually, it's very simple to me to teach on this data, because really I collect this data by myself for my board study for more than 10 years, really, for about 13 years or 14 years. So here I have also weight and height for about 539 worker in offices, in governmental offices. So this is their weight and height, okay? And there is their age range from 18 to 65, 15 or 18 years to 65. So this is their weight and height. Of course, later on I calculate also body mass index from the weight and height, but let us see how to a simple regression. Our subject is regression, and we'll take first linear regression. Then we'll take another type of regression, which is logistic regression. Logistic regression is very commonly used in medical literature, and we also will talk about it. Really, in the training exercises, they have put two sessions about regression. One for linear regression and the other for logistic. Today we'll take both of them. We'll take both linear regression and logistic regression, and probably next week we'll take survival analysis or non-parametric tests. So we are left with two subjects really, and survival analysis and also non-parametric test. Probably with the survival analysis we can also talk about diagnostic tests or rock curve, or we can also talk with non-parametric about sample size. We show how to estimate the sample size from a software. Really not SPSS, but software like Stata or MidCalc or SigmaPlot. Okay, so really we can finish our inshallah we can finish our course within. And we need 2 weeks really. We need, in addition to today, we need also another 2 weeks really, inshallah. So now let us talk about the linear regression, and here let us first graph the weight and height. So I'll graph where I already let us remove this. I would say reset. Then I start by scatter diagram. I put the scatter diagram here, and I will put the height and weight. So I put in the x-axis, I'll put the weight. I don't know, probably you find that you do that in reverse way in the exercise, in the PDF, which I given you. But here I will predict the weight. I'll predict the height from the weight. So I put the weight in the x-axis and the height in the y-axis. So this is the x and this is the y. So I'm predicting the height from the weight. This is y and this x. Okay, let's say okay. So this is the graph. This is the graph. Okay, scatter diagram. You see there is, you expect there's a relationship. Let us see, relationship not very strong really, not a straight line, but let's see, we draw the line here. So we can draw the line with this. This is the line, and yes, you can say okay. So I'll say close. Now this is really the line, okay? And this is the equation. This is the regression equation, which you will obtain by regression again. And this is R really. This is the square of R. So R really is 0.5. We square it, become 0.2. So this represents really the variability which can be predicted. The variability in height which can be predicted by the weight. Really, if R is high, R squared is higher, the better. This is called coefficient of determination. While R itself, R not squared, is called correlation coefficient. While R squared is called coefficient of determination. R not squared called coefficient of correlation. So really R squared is better than R. R squared is better. And really it means that we can predict about the variability in the height can be predicted by about more than a quarter of the variability in height can be predicted by variability in the weight. Okay, see this is a proportional line, and this is the constant. So when x is 0, this is the constant. So this is 1.38. 1.38. So this is a constant. Okay, this is a constant, or a or beta 0, sometimes called beta 0. So when the weight is 0, the height is 1.38. Okay. So we can use this equation to predict the height from the weight. Okay, not accurately, not exactly, but approximately, yes. So how we can see already given the equation, but we can obtain equation by analyze, going to regression, and then linear regression. So here I'll remove this. Let us say reset and start from the beginning. So I want the dependent variable is the height is the y. So this is dependent variable, and I want to predict the height from the weight. So my independent variable will be the weight. Okay. So of course this is a simple linear regression. Later on we'll go and put more variable in order to make it multiple linear regression. Okay. Of course there are many choices here. There are many choices here. You can put confidence interval. Can put also secretive. Can plot what's called residual, etc. Which is our difference between the real and the estimated value. Of course, the less the residual bracket is better. Okay. Now, so let us say there's of course more than one method. Usually use enter the default. But this see there are more than what's required for the we can't put this in the thesis really. What we put here probably the last table. Okay, so I will copy this into my Word file and put it and clean it and convert the font and everything. So really I don't need to put this. Probably I need only to put the p-value, this p-value, which indicates that model is significant. So my model is significant, which means that weight can predict the height. So constant is significant, doesn't matter, but this is the weight, so it is significant really. And this is the really approximation of the value. This is the coefficient really, which is here. Okay, so this is the coefficient. It is power to power -3. Really, if we can go here and make exactly what is this value, to cell property, or to number, and we increase the decimal. So okay, so this is decimal. This is really the same value here. So this is the same value. So this is the same value here. Okay, standardized coefficient mean make it a normalized, divide by the standard deviation. Okay, but this is really the equation. This is what we use in the calculation. This is the beta coefficient, and multiplied. If you have your height, if you give me your weight, I'll multiply this by your weight, then add this constant and obtain your approximate height. Okay. And this is the 95 course interval. You see that for the beta, This is the significant p-value. P-value is significant for the weight. And this is the constant interval, and it doesn't really pass through 0, and it doesn't pass through 0. And it is, both of them are really less than 0, and they are less than 1. They don't pass through 0. So it means that there is a significant relationship. Really, what probably I want to put only this in my result. Okay, I'll later on show you a result for in a thesis or in an article. So this is the ANOVA for the regression equation, and this is the significant, the model significant. Probably I write here a p-value for the whole model is p less than 0.001. Okay, so I estimated really this indicates that there is a relationship between weight and height, and also we can use weight for the prediction of So it gives us information just like correlation, but also it gives us the relation, an equation which can be used. This equation can be used to predict the height from the weight. So really, there are many examples for this. Yani, there are many examples in medical research for this. And you can use simple measurement in order to predict something that's difficult. I remember a board thesis, a board research, very early board in family medicine, done before probably 14, 15 years by a student from Baghdad, which predict really used to, so made a simple regression equation to predict the gestational age from the fundal height, and which is the height of the uterus from the fundus up to the umbilicus. So simply a simple measurement. Choose a simple measurement, which is fundal height, to predict something which usually need a sonography, which is gestational age, the age of the neonate, of the neonate, or of the fetus, fetal age. Okay, so we can use simple things to predict something which need even apparatus or equipment. So really very useful. Regression is very useful. And this show relation, it's a significant relation, and also we can, because the relation is significant, we can use it for prediction. Now, frequently also we use multiple regression. So linear regression again here, and I can use also, for example, I may also use the age for prediction of the height. But of course here, because they are all adult, really, I don't think the age will be a strong predictor. Really, if they are children, if I took children from 5 to, for example, to 15 years, really the age would be a very powerful predictor of the height, very powerful, even powerful than the weight. But here really, because they are almost real, they are adults and they have reached to their ultimate height, probably, well, the age really will not predict the height really. Probably I can put the sex here. Well, we can put other like other predictor, but if they are categorical really, and more than 3 category, we have what's called dummy coding, and you cannot, for example, these 3 categories, you cannot enter it into a linear regression. We need to go, it's called dummy coding, which means we convert the 3 groups into 2 groups which are only 2 categories. Okay, so sex really is already 2 categories, so we can enter it into linear regression. Later on in logistic regression, no, we can enter a categorical variable with more than 2 categories. Later on, we can. But linear regression, no. We should, the variable is either continuous or is only 2 categories. Okay. So again, here we can see, we say okay. And again, really, we'll go to the end. Okay. So we see here that well, really, the weight predict is a powerful predictor of the height, but also really the age, as we said, because the age they have already adults, so it is not significant. But 6 is really significant, and really it is negative. The coefficient is negative, which means that because I've coded the female as 2, so the relation is disproportional. I mean, as one become a female, it becomes shorter. So really here, the female really were shorter than males. So again, sex really is a powerful predictor of height. So I improved my equation really, and R squared improved. It was 2.7, etc. It became 5, almost 6.6. 60% of the variability can be predicted. So I improved my regression, my predictability. I can now predict height more accurately by using sex. If you go and see the let us see, explore the height by this is the height by sex, just to see the height and factor sex. See that the mean for the male is 1.71, while the mean for the female is 1.56. So obviously female are shorter than males. Therefore, it was significantly present in the equation. So we can use this relation. We can use this in the regression, in the calculation of, and in the prediction. So really now equation really can use more than, we can use the sex, also this beta coefficient, and also the weight. So we can use here 2 coefficients in order to predict. Now our equation is become really multiple regression, what's called. Yani we are really using more. So really now we are using really, this is the weight and height, and this is your PDF, train PDF. Let's see whether there is multiple linear regression. So here work stress, weight and work stress. So here I think he has introduced more another variable. I think, well, again here the same thing. It is simple linear regression. I think there is something about multiple linear regression. Well, again, this is simple linear regression. Oh, this is multiple regression. So this is multiple. So this is multiple regression. Okay, this is multiple linear regression. So you see that there's more than one x. So the equation will be, of course, more than one beta. So beta 1, beta 2. If you go to the output, this is the beta 1 for the weight, and also beta 2 for the sex. So I put the sex because it's significant. Okay, so I use the sex and the weight for prediction. Okay, so now if you give me your weight and sex, so I multiply, for example, a female, I multiply 2 by this, and also multiply her weight by this to obtain the height. And it will be more accurate. So the prediction would be more accurate if I use two variables. So this is called example of multiple linear regression. Okay. And again, the model is significant. The whole model is significant. Okay. Probably I can put the age. Really, it has no effect. Really, the age has no effect. Simply, it has no effect because all of them really, as we said, they are adults. But as we said, sex really and weight really, they are very highly significant. Okay. So the age really passes through 0, which means it's not significant. While here the constant interval doesn't pass through 0. The constant interval doesn't pass through 0, which means it is significant. Okay. Probably you may not put this in the literature or in the article. You may even not put T. You might just put the significant and the coefficient. Okay, put the coefficient.
Doctor, one question.
Belly.
For diagram, we can make diagram for the multiple linear.
Well,
How
it
we
will be
can-
really it will be complicated for يعني for simple regression, which is one variable or to one variable with other variable with one variable, it's okay. But for this really it is, I think it will be complicated. يعني you can make matrix, yes, you can make matrix, but it will be for the weight, height, weight, and age and height. You can make a matrix, correlation matrix, but as we see, you can make really, but sex you cannot really. I can make really height and weight, age, and graph. Well, this is not the graph, of course.
Graph, yes.
Really, I don't know whether the graph will be easy to draw, to put more than one variable. I don't know whether we can put more than one variable here. Let us see. Probably this one. I don't know whether we can put here the sex really. Have to try really. I don't know. I'm not sure whether it will be useful. I'm not really sure of useful. Well, really, I don't know. Not so useful. Not really. Not clear with the male and female really. So let's try again. I don't know whether we can say probably this one. So we said the height. Want to put the height and do it here. Probably I said I put the 6 spot. Age here, no, doesn't accept this really. It accept this really, but really it doesn't show us something informative. Doesn't show us something. Really,
We may can use last two.
really not so useful. Again, not so useful. We usually try graphs. You can't try many graphs here. You have really. I don't know whether really I don't know whether this one will be. Probably now it's colored. So see here. Well, I don't know whether this will be useful. So male, you see, yes, yeah, here, yes, you see the males are here on the height. Yes, they are heavier, and also they are their height is they are taller. They are, of course, this height in meter. Okay, so this really females tend to have low weights and also low heights. So this, I think this is useful. This graph is useful. I may show the line here. Okay, so this only includes sex really. Well, I think it's useful. So really graph, we should try. I think this is useful. This graph is useful really. Although the equation really doesn't include the male and doesn't include the equation is the same as with the height and weight. Doesn't include the sex. Doesn't include the sex. So in this case, really, I can remove the equation. So really, I can remove simply the equation from here. really, I think probably you can really. I'll try to move this. I'm not able really to move it. I can simply, it is not so difficult really to say this. Okay, so now you can also improve this. You can remove this and simply cancel this. Okay, so now this is okay. So now this is the graphs. Okay, now we have removed the equation because the equation is not correct really. Because it doesn't include male and female. Now we can see this. This has give us useful information because it shows the male and female, and shows also a relation between weight and height. Okay, but this is the you can put this in your thesis or article, and you can put this also. Probably I prefer that we remove the age. I reanalyze and remove the age because it's not useful. So probably I'll remove the age as not useful. So I obtain a clean equation for the weight and sex, okay, which are significant really. Okay, so this is really what's we call multiple. When you have one variable, of course you may put many variables really, and you have, for example, if I go really a study for birth weight really, just go to I think birth weight. Let's see whether I think commit medicine. Let's see. So really, let's see whether Dr. Qasim, so Dr. Qasim from UNICEF in Arabic, so he done his visit really on really on see on he has birth weight, but really he has so many variables really, and we have so many. If you see his, let's see whether you can see something here, you can understand something from his result. So you see, this is so really we have so many variables really here, and we have taken really so many variables probably. So of course, this regression we can also do linear regression, but this is really the SPS output. And how you select the variable really, how to select the variable, and this result can be put in a thesis really. It's logistic regression, but can be similar for linear regression also. Can be put like this. So we have the variable and the beta and standard error, also the test here. In logistic regression called WALD, while in the linear regression called t-test, and the significant. Also, you can put here the constant interval. I think also I think they requested from him the student really, the supervisor requested two things really, which is the same thing really. You wanted to, we did the regression, divide the weight of the child or the newborn into two groups, just normal and low birth weight. So this was the regression, as we'll talk about now. And also they requested that they do multiple linear regression. Multiple regression, just what we have done. So multiple regression, just like we have done, is significant, as you see. The model is significant, and this is really, there are many variables. Really, so there are many variables, but the significant, the quarter and the pregnancy period, gestational weight, of course, certainly gestational duration or duration of pregnancy will affect the weight. Certainly, the longer the duration, the weight of the child will be higher. and this is also number of children again affect that, and also admission during this pregnancy to hospital and mother weight effect. So yeah, really you have so many variable really, and near regression, and really he has taken in study so many variable. So how to select the variable, what we enter into the logistic regression or into linear regression. This is, again, it's a big problem because previously the literature say, well, you enter into the equation the variable which are significant with the univariate test. Yani t-test, you do t or chi-square, and you find it is significant, yani p less than 0.05 or 0.05, and then you enter it into the equation, into the multiple linear regression or into the logistic regression. Now, recently, and especially during discussion of Dr. Qasim Erbil, the great professor said to him, they discussed the three great professors really. One of them was his supervisor. So they say, well, you should introduce all the variable. They objected. They say, well, we should introduce all the variable. The problem with introduction of all the variable really, it will be very complicated. Yani. There are too many variables, and some of them, there is what's called collinearity. They are similar. For example, parity and gravity, they are the same. So this will make the model inflated, complicated, and difficult to interpret. Therefore, really, the solution was put by Hosmar and Lemishow for logistic regression. They say, well, you enter into the model the factors which are significant, and also those who are p-value up to 0.25, 0.250. So if the p-value is 0.9, you don't enter the variable. If it's 0.7, you don't enter the variable. But if it is, for example, it is 0.0, مثلا 0.25 or 0.115, 0.15, despite it is not significant, you enter it. Okay, or 0.2, for example, it's 0.2. So up to 0.2, up to quarter to 0.25, you enter the variable. If it is more than that, if it is more than 0.25, you don't enter it. Okay. So really, multiple regression, logistic regression need really time. And one time really for my study, I need 3 months to do a proper logistic regression, because frequently when I do it, they say, well, you have multi-collinearity. Your variable are similar, their number are similar, so you have to remove variable. So I continue to remove variable until I obtained a small equation, really a small nice equation. So it means that really when you do a study, you don't enter a variable which are not related, quite not related to the, and biologically not reasonable. And when you enter, also you enter into the model, you should have idea. You should expect biologically how that variable affects the outcome. And you should study every variable when you enter it into the equation. And if you cannot decide, you use this rule. You enter every variable when it's significant, and when the p-value is up to 0.25. Up to 0.25. Really, when the student, Dr. Qasim the Great, discussed the thesis, really, I didn't know this rule. So really, it was a problem for him, because he didn't know how to define himself, really. The professors asked him to enter all the variable, and while I have entered only the significant variable, which is, of course, the old literature, and the 80s, 70s, and in the 90s, even the 90s, they say, well, you enter only the significant variable. Okay? But later on, they saw that not only the significant variable are useful, but also those who are on the borderline, and up to 0.25, the p-value up to 0.25, they also can be useful. Okay? So again, this is I see this massive table يعني, to put in a thesis. But well, this is what his supervisor asked him. Ask them to enter all the variable and to see the significant variable. So now this is really a multiple regression on the actual weight. And the weight here was numerical, not categorized. Okay, so this is really the birth weight, famous birth weight study in Erbil. Okay, now let us return to our data about. And see now the other type of regression, which is very frequently used, even more than, and especially in public health, use a lot of logistic regression. Here, logistic regression, the variable is simply two categories. So here, really, originally in the physical activity study, really the categories. The questionnaire or the study classified them into 3 categories. In this case, I can do ordinal logistic regression, which is more complicated. But I wanted to do a logistic regression, so I put here the moderate activity and high activity into active category, and the not active into 0. So I simply categorize. This is what requested in logistic regression. Usually, logistic regression, the outcome is 2 categories. Okay. If you have death and life, the outcome of disease, life will be given 1, and death will be given 1. Life will be given, if the patient survived, will give it 0. While if he died, I'll give it 1. Okay, here the category really, I give not active as 0 and active as 1. Really, I could have reversed the code. But we see how we understand the output. Yani. Really, I have put that in mind when I understand my output. So here, I coded the variable into two categories. And if I want, for example, I want to do, if my dependent variable is body mass index, then probably I will categorize them into categories normal, and below 25, I will give it 0. And those who are overweight and obese and everything above 25 and above, I will give it 1. So usually you need to categorize the variable into 2 categories in logistic regression. So logistic regression means there is 2 categories. The outcome, the Y, is 2 categories. Okay. Here, when the Y is 2 categories, you cannot analyze by linear regression because some of the edge ratio will go, and will not be meaningful, will be less than 0, will be meaningful really. You cannot understand the result. So the result, the solution is to do what's called logistic, or logarithmic, to convert the outcome into logarithm, the 0 and 1 into logarithm. So this is the mathematics of logistic regression is logarithmic conversion. Okay. Now, so again here, I think in the, well, this is the, I think this is the PDF for the linear regression. If you remove this, really the next will be, this is a training module. I think this is the, will be the logistic regression. So this is the logistic regression here. This is the PDF. So this is the, I think that, so you see that the outcome variable should be, dependent variable should be only 2 groups. Okay, as we see here, I will do it here on my data. So it's all my data. I will do here. So I said the variable here, which I use. We have 3 categories. We said we don't use this unless we want to do ordinal regression. But since this is my dependent variable, and I want to study the effect of other variable on this independent variable. So I go here to logistic regression, logistic binary logistic regression, binary. Okay, so really I have done already. I was doing it before the before the lecture. Well, let's reset. Now I want here to put the independent variable should be two categories. One of them is 0, 0, 1. 0, 1. Usually I put 0, 1. We may accept 1, 2, but well, previously the software doesn't accept only 0 and 1. I think now it's accept 1, 2, but I prefer to put 0, 1. Okay, so this is 0, 1. This is the dependent variable. Now I want the independent variable, which I should have studied. I should have analyzed with the univariate test. I should have idea about. Okay? Not to enter any variable or a variable. It will be very crowded. It will be understandable. So I know now. I have idea about. I've already analyzed with the chi-square, with the t-test. Already I have idea about the variable. So I enter the variable which are really significant, and I believe probably it will give me prediction of the physical activity, and also it give me relation and to exclude confounding variable. Confounding variable means the variable which are significant by chi-square or t-test, but they are not real. They are due to relation of other variables. Yeah, they are confounded. What's confounding? Dr. Kaisar will give you a lot about confounding. So really, regression again useful in exclusion, not only in the prediction, but in exclusion of the confounding variable and in maintaining the significant real independent variable, the truly independent variable which affect the outcome. Okay, now here, of course, we can enter the age as a categories or as a categories or as a continuous. We can. I will, for example, enter sex, enter also the job. Really, I know really sitting time certainly affect the result. Okay, well, body mass index really I haven't found it useful. Oh, we can enter it really, it will not be significant really. We can enter it and not be significant. Okay, now really I will. So really there are several methods. Use the default really. Really, there's a step here called categorical. Really, is important. What are the categorical variable here really? There are two here, sex and job really, and really automatically, really SPSS will consider one of them as indicator or reference variable, and the other is the variable which give odds ratio for it. So here let's put it as it is, and later on we'll see. Probably we can change it, of course. We can change probably I can make the indicator for sex I can make the male, for example, is the indicator, and see result for the female. Okay. Now I will say continue. Probably something I want to do also to see the constant interval for the XP, which is the odds ratio. Probably I want this classification plot. Okay. Let's see. And this is really the test for Hosmer. They have a book really on logistic regression. Hosmer, let me show goodness of fit test. You can put it here. Then we say okay, and really, so there are really a lot of results really, but we don't put them all of them in our thesis really. What we put here really is we go to the last method really. So this is his modeling show. It is significant. Well, it is really, it's not significant. It is in the it's more than 0.05. Really, I need to read about the Hosmer show tests. But what I know is really is this equation really, is this equation. This is very useful equation. Again, this the log likelihood again give us idea about the significance of the model. But let us see that really these are the equations. The equation, this is what I want to put in my thesis really. And you see that the age is not significant, sex is not significant, job really is significant, job is significant really. And again, this sitting time is significant, body mass index not significant. So really, these are the odds ratio. And you see, this is not significant, not look to it, but probably I will try to understand these. Both of them, the odds ratio is less than 1, which means it is really protective. So it means that really the category compared to the reference value, the other category is protective. So here the reference category was non-teaching, so the non-teaching, so they are the category is teaching, and it's protective against being inactive. And again here again sitting hours was significant. So of course here the variable, it means that the more sitting, the less sitting mean that you are active. The less sitting, you are active. Okay, of course every variable really, every coefficient, we have to think of it carefully, and how and understand it. And it's not easy really to understand logistic regression, really not easy. And you need to carefully understand how we have coded the variable and what the meaning of this, what mean protection mean, and protective. This is odds ratio less than 1 mean protective, and both of them really consider both of them less than 1. They don't pass through 1. This again, they don't pass through 1. This is the other constant interval of the odds ratio. They pass through 1. For all of them, not significant. They pass through 1, but these are significant. So these are really, they are significant, and they are both of them less than 1, which means they are protective. So it means how to understand protection. Yani. So here really I understand it by the job has been classified into teaching and non-teaching. So being really teaching staff is protective against being inactive. Okay. Again here they can again sitting hour, less sitting hour is protective against being inactive. Okay, so really this is logistic regression, yani. And I think here let's put example. Really you can go here and step by step and see how he do and interpret the. You see here is this is the dependent variable, so it is usually 0 and 1. And this is the, you see the significant, and this is the log likelihood ratio, and this is the classification table. This is what I want really to give us how our model classify correctly. And this is the equation. This is the most important equation. And here we look to this. We look, so this is the third category was significant, and this is really the constant. The odds ratio was really above 1, which means it is risky to have this category. Increased risk, there's increased risk, and the really difference doesn't pass through 1, which means it is significant. Well, this one passes through 1. This one passes through 1. So only the third category was what, septic later on. You can later on read about this exercise. But I mean, this is really here's the odds ratio was risky, not a protective, like in our example. I obtained here a protective odds ratio. While in this example, this is a risky odds ratio, and it does not pass through 1, which means it is significant. Again, from a p-value, it's significant. Okay, this is really what we want to do, put in a thesis. Okay? So, you see, this is probably this again another example. Let me show you. Probably we are almost finishing, but let me show you probably what I've done that in a thesis. Again, in one thesis, I've shown this probably. Let's see the result here. For this really was a study about knowledge on weight during pregnancy, or gain of weight during pregnancy. So this really was the last result was a logistic regression. So of course there are many tables. So these are the results are really here. You are describing the sample. I'm describing the sample, and I'm making some univariate analysis, chi-square, etc. Univariate analysis. So I'm making univariate analysis really. I'm testing the. I'm not doing. I'm doing chi-square. So I'm getting idea about the variable. I'm getting idea about the variable, so that at the end I will enter them into a logistic regression equation. So these are all chi-square, which give me idea about which is the significant, or which variable I have to introduce into a logistic regression. So you see these are, and then I reach to the end. This is the logistic regression. So we classify knowledge into there is knowledge and there is no knowledge, or no knowledge and good knowledge. So it's 2 categories: the knowledge on socio-demographic, so knowledge, level of knowledge, and the outcome are the socio-demographic variable and body mass index. So these are the result, and you see this is the beta, the coefficient, and the standard error, and the p-value, and the odds ratio. These are odds ratio and confidence interval. So for example, here's the age was categorized, and you see that young age was significant. And young age, young woman, they don't know, they have lack of knowledge. So young age is associated with this age from 15 to 25, 24, to less than 25, associated with poor knowledge of weight increase in during pregnancy. Again, well, residency was not significant really, was not significant. Well, education was, again, especially illiterate was significant. So illiterate really, they have poor knowledge. They have poor knowledge, so they are at risk of poor knowledge. So they are at risk. They are at risk of poor knowledge about weight increase. If we come to body mass index, well, employment was not significant. Body mass index really, those who have overweight, again, they have poor knowledge. See, they have poor knowledge. They don't know the area, and therefore, of course, they are obese. So they have poor knowledge about about the risk of increase in weight and the problem associated with increase in weight during pregnancy. And you see, for every category, usually we put the reference group. So this is compared to overweight obese compared to the normal. Okay, so. Well, I think the reference group was put underweight compared to the underweight. While in education, the reference group was higher education. Okay, so in for example, in residence, the reference group was urban. It was not significant. While the reference group in age was more than 30 years. They have more experience. So we put them as a reference group and compare to them the younger age group. And really, we discovered that the younger age group have lower knowledge, or they are at risk of low knowledge. So this is logistic regression, and it is very useful in studying relation between a factor between an exposure, between exposures, factors, and an outcome or an dependent variable. Okay. So this is, of course, the subject really is big. I know it is a big subject, and logistic regression is a big subject, and there is a lot of math here, but we haven't taken really the math. We simply do it with the software. Okay. So this is, I think, if you read the PDF, you probably you'll get better idea about the logistic regression and linear regression. Okay. Really not easy topics, but as we said, they have become classical. And linear regression and logistic regression, they have become classical, and now they are really using more advanced vision. Now they are using artificial intelligence and machine learning. Now logistic regression and linear regression become all techniques, all the statistical techniques, and everyone is using them. Everyone can use them with the computer. Previously, it was very difficult. Now it is easy, very easy to use logistic and linear regression. But what we want that you do it correctly. And some may misuse it. For example, their outcome is logistic and they use linear. I have a paper already come to me for evaluation from physician. They are very clever. However, they have simply done, they have two outcome really, two outcome. The outcome is two categories, and they have done linear regression, which is wrong. Or they have a categorical outcome, and they do, for example, they have logistic. Logistic is only two categories. If you have multiple categories, you have to do another type, which is called ordinal logistic or multinomial regression, etc. Okay. Well, I hope that's useful to you. I think some of you will use it. Will use that. Will use regression or linear regression or simple linear regression, or one variable or multiple linear regression or logistic regression. Some of you will need that in your study. Okay. Of course, even we can apply that on the lead set, that data set on lead. You can put that. You can use it to predict the renal function from lead, from sex and body mass index. You can try that if you want. If you want to train yourself. Okay. Okay. Thank you very much. Well,
thank you.
I have you that will be useful to you. I hope it will be useful to you. As I said, probably if you will have two weeks, we'll finish the subject. We'll finish our course, inshallah. And of course, probably next week we can also discuss your result also.
دكتور هو حضرتك أي يوم تريدها؟ يعني
ما مشكلة. we said second week of the, not this week, next week.
So it's not on Sunday.
No.
Okay.
We can discuss after 2 weeks. No مشكلة لينا.
Okay.
Just an exercise for you. Exercise. Try to read and do exercise for you. Try to make analysis, just like you have done. Okay.
Inshallah.
Okay. Now I will leave you. موفق بين إن شاء الله. خاطر هوا. Okay.
دكتور.
موفق بين.